Today, we're going to see what happens when you take a universal language for data and pair it with the incredible power of artificial intelligence. And what are they aimed at? Oh, just one of the biggest energy hogs on the entire planet, our buildings. So I want you to just start with this question rolling around in your head. What if our buildings could actually help design themselves? What if an AI could optimize their blueprints for sustainability and comfort, before a single brick ever gets laid? Because, let's be clear, the problem we're facing is enormous. The construction industry, plus all the buildings we live and work in, are responsible for a truly staggering 39% of all global energy consumption. That's a huge slice of the pie, and honestly, a massive opportunity to do things better.
But to really tackle this, first we've got to understand that the problem isn't just about steel and concrete. Nope, it's a digital problem. It's all about the data.
Just think about it for a second. You've got brilliant architects, brilliant engineers, and brilliant energy analysts, but they're all working in their own separate digital worlds. The software they use is incredibly powerful, but it doesn't speak the same language. It's kind of like having a room full of the world's best experts who can't understand a word the others are saying. This creates these invisible walls, these data silos that make a truly holistic, efficient design basically impossible.
So let's break down this communication gap. On one side, you've got architectural software, what we call Building Information Modeling, or BIM. It's all about the physical stuff, geometry, materials, space. The goal is to create a perfect digital twin of the building. But then, on the other side, you have the energy simulation software. It's focused on totally different things, like thermal properties, climate data, and HVAC systems. They have different goals, they use different data models, they're just fundamentally incompatible.
So, the first step in the solution is, well, it's actually brilliant in its simplicity. We need to build a universal translator. We need a way to bridge this gap so that all this crucial data can finally flow freely between these different worlds. And this is where semantic web technology comes in, specifically something called the Resource Description Framework, or RDF. The easiest way to think about RDF is as a kind of digital Esperanto. It breaks down all the super complex information about a building into a simple, standardized format, a web of interconnected data points that any piece of software can read and understand.
Now, the real magic happens when you create a kind of translation dictionary made of what researchers call mapping patterns. These are basically the grammar rules for this new universal language. A simple rule might say, okay, when an architect's software mentions an IFC building, the energy software will understand that as a SIM building. It turns out, by creating just 14 of these core rules, they could translate almost any concept between the two digital worlds.
So the whole process looks like this. First, you take the architect's design and convert it into that universal RDF format. Second, you apply that dictionary of mapping rules we just talked about. And third, you use automated queries to do the translation. And just like that, poof, the digital walls are gone. But once the data can finally talk to each other, that's when you can bring in the real powerhouse, an AI that can read everything and actually start making decisions. It's time to train our AI architect. Now, the model they used has one of those super long, complicated names, so let's just call it our AI architect. What's important is that it's a hybrid system. It combines an AI that's great at making predictions with another one that's amazing at searching for the best possible solution out of thousands or even millions of options. Its job is to take all that unified data and just constantly tweak the variables to find the absolute best design combination possible. And here's the crucial part. It's not just optimizing for one thing. It's juggling 4 different and sometimes competing goals all at once. Of course, it wants to slash energy use and carbon emissions, but it also wants to make sure the people inside are comfortable and that there isn't a lot of visual discomfort from things like glare. It's a really complex balancing act.
So, to prove this wasn't just a cool idea in a lab, the researchers applied this entire system to a real-world project, a huge 5-story university building in Wuhan, China. So yeah, this wasn't some toy problem. This was a complex, real-world design challenge.
So after all that, after building the universal translator and training up the AI architect, what happened? What does the blueprint of tomorrow actually look like when an AI gets to co-author it? So how much of a difference can this AI-driven approach really make? Let me tell you, we're not talking about small, incremental improvements here. The results, well, they're dramatic.
Okay, first, let's look at the baseline. This is the initial, human-led design for that building in Wuhan. As you can see, high energy use, high carbon emissions, and a pretty high level of discomfort for the people inside. This is our starting point.
All right, now watch what happens after the AI architect gets to work. Energy use absolutely plummets. Carbon emissions are slashed, and thermal discomfort for the occupants drops way, way down. The visual difference is just stunning, isn't it?
Let's put some hard numbers to that because they're incredible. The AI's optimized design cut overall energy consumption by more than 32%. It slashed carbon emissions by nearly half. And get this, it improved thermal comfort by a whopping 60% and even cut glare by over 15%. I mean, these are truly transformative gains.
So you might be asking, how did it do it? Well, when they looked under the hood, the analysis showed the AI focused on two key areas: the air conditioning settings and the building's outer skin, so things like its insulation and the ratio of windows to walls. And this is exactly where an AI just blows us away. It can calculate the ridiculously complex interplay between dozens of variables at the same time, finding that perfect balance that would be almost impossible for a human to find just through trial and error.
And this is why this is such a big deal. This isn't just a story about one building in Wuhan. It's a proof of concept for an entirely new way of designing our world. By combining a universal translator for data with an AI architect for optimization, we now have a repeatable, scalable blueprint for creating the sustainable, comfortable buildings we so desperately need.
Ultimately, this framework proves we can break down those digital barriers and use AI to solve these incredibly complex real-world problems. And it really forces us to ask a much bigger question. If AI can help us design smarter buildings, what can't it help us build?